Linearizing data is basically the process that we use in physics to take graphs that maybe aren't a linear relationship and actually turn them into one that we can use. And the main reason that we want to do that is because we really want to focus on this nice equation here, y equals mx plus b. What that's going to be able to do is that's going to give us a slope, the m, that we can then use to figure out useful information regarding experiments that we run. Examples of this would be if we are doing certain labs, and let's say we do come up with a linear relationship. So an example of that would be using Newton's second law, where you're going to graph force on the y-axis and then mass on the x. And basically what you would get is you would get a graph that looks something like this. And we would be able to use that y equals mx plus b and then plug in the variables that we're using for both our independent and dependent variable, where on our y we plug in our force, m is my slope, and then x is my mass. And what we would see then is we would see that y goes with force, x goes with mass, and then the slope here would be this unknown here, which obviously we know F equals ma from our knowledge of Newton's second law. So the slope of this line is acceleration. And so we would be able to see that the acceleration and determine what the acceleration is based on this graph using that y equals mx plus b. So that's a really nice relationship, and us using that equation of a line is really helpful to be able to figure out what that unknown slope might represent. Unfortunately, in physics, not all relationships are nice and linear, so the process of linearizing that data is what's going to actually help us to understand and be able to convert them into a graph where using y equals mx plus b is actually possible. So an example of that. Okay, so how are we going to use that in actually creating and being useful in terms of graphs that aren't linear? Obviously, sine is something that is not very common, but some other common scenarios that we have is the first one is inverse. And you're going to get an inverse relationship basically when you get a graph that looks like that. And so what you would want to do is you would basically want to plot basically y versus now instead of x, you'd have to convert it to 1 over x. So you would take your data, just like we did in the thetas, and instead of multiplying them by sine, we would take our x values and we'd just plot the inverse. And that's how you should be able to then get a relationship that is linear. Inverse square looks very similar to that of an inverse graph, but in this case, probably not that square, but essentially in this case now, and if we get this graph when we plot x versus y, what we'd want to do is we would want to plot y versus 1 over x squared. So examples of that would be like Coulomb's law or universal gravity, where basically you have F equals capital G m over r squared. That would be an inverse squared relationship where F is an inverse square of r. So, over here would be F, this would be r, and so to create a linear graph, we instead would want to plot F versus 1 over r squared, right? And we then get a linear graph that we can then use y equals mx plus b on. A square root graph would look something like this, where obviously if I plugged in y and x, see, I would get a graph that looks like that. And so here, what I would want to do is plot y versus x to the 1/2, or the square root of x. And then a last one that's not on here would be an exponential. Right, and basically that would be a graph that might look like this, where obviously that's not a linear relationship as well. So here what we would want to do is we'd want to plot, instead of y versus x, we'd want to plot y versus x squared. And in that, then we'd be able to get a linear relationship. Is what we see here. So what we see here is using the relationship of index of refraction. And basically what we're going to have is we're going to have two angles. So your setup that you would have is you would have pretty much a piece of glass, and you would shine a light into that piece of glass. And what you would notice is that that light, when it enters that glass, is going to bend, and then it's going to come out. So basically what you have is you have the bending of light, and what we would do is we would measure these angles. So this angle here would be theta 1, this angle here would be theta 2. And so if we were to graph that relationship, like we did up here, and just measuring theta 1 versus theta 2, we get the graph here. So theta 1 is on my x-axis, theta 2 is on my y-axis, and we can see that it's clearly not a linear relationship. We get this bending here at the end. Well, what we found is through experimentation, how can we create a nice relationship is that we can actually use the sine of each angle. So if we take the sine of the first angle, theta 1, and the sine of the second angle, theta 2, and we graph those, we get this really nice linear relationship between those two graphs. And obviously notice that our trend line here doesn't go through each data point. It's kind of an average of what they are. But using that, we can then create an equation of y equals mx plus b. Now, if we write that equation out in terms of basically what we have is we have sine of theta 2 equals m and then sine of theta 1, right? And what we can look at is, well, if we understand Snell's law, which is basically n sine theta, so this would be n1 sine 1 equals n sine theta, and this is n2 sine 2. Basically what we can do is we can use this, and if I can take this equation here, and I can plug it in for this equation here. And basically if I do that, what you get is you get sine theta 2 equals sine of theta 1. And okay, so what is this m then? What does that relate to? Because obviously this is y equals mx, right? And so we can see if we take this equation here, then what we have is we have n1 over n2, and that's what that slope would represent. And so I would be able to find then the index of refraction, which is considered n1 or n2 of this glass block. Because if this n1 is 1 because it's air, and then I could say, okay, I would take this slope here of 0.0694, plug it in, equals n1, which is 1. Oops. Which is 1 over n2, I would be able to figure out what n2 is. And so it's a great way to take data that we have and be able to use that to be able to figure out some unknown.